We have four really cool papers. The first one is about make significant progress on a basic open problem related to locality sensitive hashing, or LSH. So as you know, LSH is this technique for building a data structure that can answer approximate nearest neighbor queries efficiently. Very important both in theory and practice. And it roughly works by applying a random hash function to points in the data set, and the hash function has the property that it maps nearby points to the same bucket and faraway points to different buckets. And the quality of the hash function, the family of hash functions used is captured by the so-called LSH exponent, which determines the query time and space usage. And roughly speaking, the query time is the time to evaluate the hash function times n to the LSH exponent. So, in 2006, Andoni and Indyk obtained optimal LSH exponent. This is for the Euclidean case, using a fairly expensive ball partitioning approach. But basically, the problem with this is that the computation of the hash functions is quite expensive, as well as the storage. They also, in their paper, looked at a more practical scheme where each hash function maps a data point to the closest point in a randomly perturbed, well-chosen Euclidean lattice. And they showed that this method works much, much better in practice, but they weren't able to prove good bounds on its LSH exponent. So this paper shows that there is such a scheme that achieves optimal LSH exponent, and using a bunch of really cool techniques and the probabilistic method, they basically build this formal connection between LSH and nice lattices that work for this purpose, and essentially leave open the problem of actually making this practical and constructive. The second paper in this session considers k-means clustering. So this is where you're partitioning your data set into k clusters. Each cluster is defined by a center, and the points in the cluster are determined by which center is closest to them. And this is finding the optimal k-means clustering, which minimizes the sum of the distances to the center points, is NP-hard. And it's even NP-hard under margin type assumptions, where you assume that every point is quite a bit closer to its actual center than to the other centers. And so this kind of motivated considering the problem rather than in this unsupervised setting, in a semi-supervised setting, where you can make queries of the form, do these 2 points belong to the same optimal cluster? And what Ashtiani et al. Showed was that in this model, you can solve k-means efficiently using relatively few queries of this type under a margin assumption. And the new paper considers the same question in an approximation setting, and using some very clean and intuitive ideas, develop a p-task without any margin assumption, and the number of queries as no dependence on n, the size of the data set. And they prove that this is essentially optimal under the exponential time hypothesis. The third paper in this session looks at edge estimation with independent set oracles. So there were some earlier work which considered the question of estimating the number of edges in a graph using local queries. For example, what's the degree of a node? Is there an edge between these two vertices? And so on, such queries. And one of the results in these papers is that subpolynomial query complexity is not achievable using such oracles. So this paper considers two kinds of much more global queries, like, for example, is this set of vertices an independent set? Or are there any edges between set of vertices A and disjoint set of vertices B? And what they show is that such global queries allow for much better query complexity. In particular, for example, with the bipartite independent set oracles, they need only polylogarithmically many queries. So it provides an interesting contrast between, graph parameter estimation using global queries and local queries. And they have some nice applications. And what's kind of cool about their applications is that in their applications, actually implementing these oracles is very efficient. Okay, and the final paper in the session considers the query complexity of min-cut and min-st-cut. and using cut queries. So specifically queries of the form, given a subset S of vertices, what's the size of the cut between S and S complement? And what they do is they present, beautifully simple, clean algorithms for these problems with subquadratic query complexity. So for example, for global min cut, essentially linear queries, and for ST min cut, again, subquadratic number of queries. And this is perhaps surprising since n-squared queries are needed information theoretically to learn the graph. And also, one of the motivations for their work was that n-squared is the state-of-the-art upper bound on the query complexity for the more general problem of submodular function minimization. So they leave that bigger open question related to that problem open. It's a really great problem and great set of papers in this session. So without further ado,